All right, let's get right to it. Welcome back, fellow students, to the ultimate exam review explainer for electrostatic potential and capacitance. If you're gearing up for finals right now and you need to synthesize weeks of frankly pretty complex physics into a clear, actionable understanding, well, you are in exactly the right place. We're going to break down the invisible forces of the universe and see how they're engineered into the devices we use literally every single day. Okay, let's dive into this and set up our focused study plan. So, think of this agenda as our syllabus and roadmap for acing the finals. We are logically progressing from the invisible rules to engineered power. First, mapping the invisible landscape. Then, material responses and rules. The capacitor charge trap, system design and circuits, energy storage and discharge, and finally, a final exam cheat sheet.
Okay, Section 1. Mapping the invisible landscape. Before we can build any circuits, we really have to understand the invisible rules of the universe.
Let's kick things off with a core definition you absolutely need for the test. Electrostatic potential. It's the intrinsic potential energy of space itself, per unit of charge, mapped completely independently of the specific charge being moved. Now, understanding this definition is absolutely crucial. Why? Because it separates the environment, the field itself, from whatever object is moving through it. You know, it's kind of like mapping the steepness of a hill without worrying about whether a giant bowling ball or a tiny marble is the thing rolling down it.
And this brilliantly illustrates exactly how we make that map. Remember, electrostatic forces are conservative. Look at the work done moving a positive charge from point R to point P. Pushing a charge against the electric field requires external work. But, and here's the kicker, that work isn't just lost. No, it's conserved. It's stored as potential energy, completely independent of whatever crazy path you took to get there. By dividing that stored energy by the specific charge, boom, we define the potential of that space.
Now, listen up, because right here is a massive exam trap warning. Seriously, do not mix these two up. The electric field, which is force per unit charge, falls off at a rate of 1 over r squared. But potential, which is energy per unit charge, falls off at just 1 over r. When you're rushing through a calculation during the final, confusing that square of the distance with the linear distance is, hands down, the easiest way to lose points. Don't fall for it.
Now, what's really interesting about this slide is how the geometry visually locks in that exact difference. You can see the white line representing the electric field decays so much faster than the amber line representing the potential. And hey, if you're dealing with a dipole, where you have a positive and a negative charge, that field decays even faster because the opposing forces cancel out over distance. Seriously, just burn this graph right into your memory. Which brings us to equipotential topography. Think of those yellow rings as perfectly flat paths wrapping around a mountain. Because the potential is constant everywhere on that specific surface, moving a charge strictly along one of these yellow rings requires absolutely zero work. Zero! This is a super frequent conceptual question on multiple choice exams, by the way. Just remember, electric field lines always cross these surfaces at perfectly perpendicular angles, flowing downhill in the direction of the steepest decrease in potential. Moving right along to Section 2, Material Responses and Rules. Let's see how physical materials actually react when we place them into these invisible landscapes we just mapped.
Okay, if you see a metal conductor on the exam, this right here is your rapid-fire memorization list. Because conductors have these highly mobile, free-moving electrons, they enforce strict boundaries instantly. The rules: the electric field inside is always zero. Any net charge immediately rushes to the exterior surface. The field just outside is purely perpendicular, and the entire volume and surface share a single constant potential. Those mobile electrons, make sure of it.
But what if we don't have free electrons? Well, insulators, or dielectrics, behave totally differently. When you subject them to an external field, their tightly bound molecules stretch and polarize. The negative sides get yanked one way, the positive the other. And this alignment actually creates an internal opposing electric field. So the result, the net electric field inside the material is severely weakened. Though actually, scratch that, it's not completely zeroed out like in a conductor. It's just weakened.
I want you to literally take a mental screenshot of this diagnostic table right now. It perfectly synthesizes how materials dictate our engineering applications. Conductors use their free electrons to completely block and cancel fields. Dielectrics, on the other hand, use bound, localized polarization to merely resist and reshape them. This difference isn't just neat trivia. It is the absolute fundamental basis for how we build electrical components. Let's move to Section 3 and see how this builds into the capacitor charge trap. we're going to look at how we actually trap these fields using the materials we just defined.
So, by separating two large, oppositely charged conductive plates by just a tiny little distance, we create a literal trap for the electric field, and that is a capacitor. Capacitance measures a system's ability to store charge per unit of voltage. To make it super simple, it's like a water tank. The charge is the water, the voltage is the water pressure, and the capacitance is the physical size of the tank itself. The larger the area of the plates, or the closer they are together, the bigger our tank gets. But hey, we can kind of cheat the system using a dielectric multiplier. This is the ultimate engineering hack. If you insert a dielectric medium right between those plates, its polarized molecules weaken the internal electric field, and because the field is weaker, the potential difference, the voltage, drops. So for the exact same amount of stored charge, we've just dramatically increased the system's overall capacitance by a multiplier known as the dielectric constant, K. Pretty brilliant, right? All right, Section 4, System Design and Circuits. It's time to network our discrete components together, which honestly is where the heaviest math on the exam usually lives.
When we start connecting capacitors together, the geometry strictly dictates the rules. In a series combination, they share constant charge, but the voltage splits across them. In a parallel combination, it's flipped. They share constant voltage, but the charge splits up. If you just break down the logic of what stays constant versus what splits, you can easily derive these equivalent formulas on the fly, rather than just blindly memorizing them and hoping for the best.
And here is your absolute biggest exam trap for circuits. Look at the equivalent formula for series capacitance. 1 over C equivalent equals 1 over C1 plus 1 over C2. Adding capacitors in series actually decreases the total capacitance. But the most common error is that students do all the fraction math perfectly and then they completely forget to flip the final answer upside down. Seriously, guys, always remember to invert that final fraction.
Okay, deep breath. Section 5, Energy Storage and Discharge. Let's focus on the actual power we've trapped inside our engineered systems.
I really want you to commit this crucial concept to memory. A capacitor doesn't just store charge, it stores the work done to separate that charge. So the crucial point here is this. Stop thinking about capacitors as just a bucket holding a bunch of electrons. You've got to shift your perspective. A capacitor is essentially a battery of physical work suspended in tension. Let's actually look at the physics of the story here. When you charge a capacitor, you're transferring electrons bit by bit from one plate to the other. But as more charge builds up, the repulsive force grows stronger and stronger. Pushing the next electron onto that plate requires even more external work. But that work isn't gone. It is locked into the electric field itself as electrostatic potential energy, just waiting, ready to be unleashed in an absolute instant the second the circuit is closed.
To actually calculate that stored energy, you have 3 equivalent formulas, all just based on substituting our basic capacitance equation. Here is a massive study tip for you. Depending on the specific exam problem, look for the variable that is constant. If voltage is constant, use 1/2 CB squared. If charge is constant, use Q squared over 2C. Just picking the right formula right out of the gate is going to save you massive amounts of time.
And finally, Section 6, Final Exam Cheat Sheet. Congratulations, study buddies, we made it to the end. Let's tie it all together. Behold your one-page cheat sheet, the synthesis pipeline. Literally everything we've covered today follows this exact journey. We started with the abstract inverse square forces of isolated charges. That's the theory. Then we mapped their potential energy to understand the landscape. We learned how conductors and dielectrics react to provide control. We engineered the geometry to create the capacitor trap. And finally, we networked them into applications, the engines of modern circuits. From the flash in your smartphone camera to the RAM in your laptop, everything relies on trapping and discharging these invisible forces. You now have the complete roadmap to understand it all. So, as you head into your exam, ask yourself, how do these fundamental electrostatic traps power the modern engines of our daily lives? Because acing this final, that's just the very first step to engineering the future. Good luck studying, you've totally got this.